In the previous section, we discussed how a particle-wave duality is an intrinsic property of light. It's now 1923, and a graduate student named Louis de Broglie made an extraordinary suggestion. He thought that if light, a wave, could behave like a particle, then maybe a particle, like an electron, could behave like a wave. De Broglie proposed that all moving matter has a wavelength associated with it, just as a wave does. He made the explicit proposal that the wavelength lambda of a particle is given by the same relation that applies to a photon. This is known as the de Broglie wavelength of a particle. H is Planck's constant, and p is the particle's relativistic momentum. The first confirmation of de Broglie's suggestion came in 1927, when American physicists Clinton Davison and Lester Germer directed a beam of electrons at a crystal of nickel. The kinetic energy, and thus the momentum of the electrons, was chosen so that the de Broglie wavelength of the electrons was on the order of an angstrom, or 1 × 10⁻¹0 meters. Recall that this length is roughly the spacing between atoms in a solid. Therefore, if the electrons were to behave like a wave, we would expect to see diffraction effects just as we did with X-rays. Indeed, this is exactly what was observed. Particles other than electrons can also exhibit wave-like properties. For instance, neutrons are routinely used in diffraction studies of crystalline matter. The figures compare the neutron diffraction pattern and the X-ray diffraction pattern caused by a crystal of rock salt, or sodium chloride. Although all moving particles have a de Broglie wavelength, the effects of this wavelength are observable only for particles whose masses are very small, on the order of the mass of an electron or a neutron, for example. The de Broglie equation for particle wavelength provides no hint as to what kind of wave is associated with a particle of matter. To gain some insight into the nature of this wave, we turn our attention to the following figure, where part A shows the fringe pattern on the screen when electrons are used in a version of Young's double-slit experiment. The bright fringes occur in places where particle waves coming from each slit interfere constructively, while the dark fringes occur in places where the waves interfere destructively. When an electron passes through the double-slit arrangement and strikes a spot on the screen glows at the spot, and parts B, C, and D of the figure illustrate how the spots accumulate in time. As more and more electrons strike the screen, the spots eventually form the fringe pattern that is evident in part D. Bright fringes occur where there is a high probability of electrons striking the screen, and dark fringes occur where there is a low probability. Here lies the key to understanding particle waves. Particle waves are waves of probability. Waves whose magnitude at a point in space gives an indication of the probability that the particle will be found at that point. At the place where the screen is located, the pattern of probabilities conveyed by the particle waves causes the fringe pattern to emerge. The fact that no fringe pattern is apparent in part B of the figure does not mean that there are no probability waves present. It just means that too few electrons have struck the screen for the pattern to be recognizable yet. The pattern of probabilities that leads to the fringes in the figure is analogous to the pattern of light intensities that is responsible for the fringes in Young's original experiment with light waves. In section 24.4, we showed that the intensity of the light is proportional to either the square of the electric field strength or the square of the magnetic field strength of the wave. In an analogous fashion, in the case of particle waves, the probability is proportional to the square of the magnitude psi of the wave, where psi is referred to as the wave function of the particle. In 1925, the Austrian physicist Erwin Schrödinger and the German physicist Werner Heisenberg independently developed theoretical frameworks for determining the wave function. In so doing, they established a new branch of physics known as quantum mechanics. The word quantum refers to the fact that in the world of the atom, where particle waves must be considered, the particle energy is quantized, so only certain energies are allowed. We will see that in order to understand the structure of the atom and the phenomena related to it, quantum mechanics is essential, and the Schrödinger equation for calculating the wave function is now widely used. In the next chapter, we will explore the structure of the atom based on the ideas of quantum mechanics.